So when we're going through our double replacement reactions, or that M word replacement reactions, what we want to go through and do is identify your cation and your anion in each species and just exchange those. Okay? So in our first one, our cation happens to be lead, and our anion is nitrate. Why is there a 2 next to the nitrate? Okay. That 2 is there to balance the lead. Lead has a +2 charge, so we need 2 nitrates to balance the lead. That is the only reason there is a 2. It's to balance that formula. And the next one, we've got our potassium as our cation and our iodide as our anion. So we can go through and do the exchange. I'm going to exchange the cations for no particular reason. And I would end up with my potassium and my nitrate. And this is where nomenclature can come in handy. You'll notice I'm just saying potassium and nitrate. Why am I not shifting the 2? Okay, when we look at this formula, right, there's a 2 in the lead nitrate. Why do I not shift the 2? Okay. It has to do with the meaning of what the 2 was. What is the meaning of the 2? To balance the charge of lead. In potassium nitrate, is there lead anymore? No, so I can't carry that 2 across. Interestingly enough, I did carry another number across, though. I carried the 3 across. Why did I carry the 3 across? That's what makes nitrate nitrate. If I don't carry that 3 across, it's the same as saying for our very next one, lead iodide, where it's Pi. Okay. It has to be Pb. Why? That's the symbol for lead, Pb. The 3 is just as much a part of the name nitrate as the B is part of lead's symbol. Okay? It is odd because we end up now shifting numbers and letters differently depending on the situation we're looking at, which makes it tricky. Okay? Before we go into balancing the equation, and this is where again you need to pause, check your products. Did you balance your products first? Not the equation, but look just at that product. What is the charge of potassium? +1. What is the charge of nitrate? Is that product balanced? Yes. What is the charge on lead?
+2.
It's a little bit tricky. How do you know it's +2?
Because it changed.
We can go back to our starting material and realize that lead started at a +2. We are running under the assumption that it did not change in the course of the reaction. So lead carries a +2 charge. Iodide carries a -1. Is our charge balanced? No, which means we need to fix that by putting a 2 as a subscript right after the iodide. Okay? Yes?
I just wanted to clarify, it doesn't matter whether it's PbNO3 or KI plus PbNO3, it doesn't matter what order.
It does not matter the order on these. Addition is communicative, so it doesn't matter the order we do it in. I would argue that before we move on, we've got one more step. We need to specify our phases. How do we determine our phases? Our solubility rules. If you spent that time since the last lecture and memorized the one that I told you to memorize, potassium is a group 1 metal, which means that first species is aqueous. Now, in all honesty, if we tried to pull this based off of my memory skills, I'd just be guessing for the next one because I don't have that memorized. Right? So we could pull up a solubility table, and what's the solubility table tell us? It's a solid. Okay? It's insoluble is typically what it says. Insoluble as a phase is solid. Okay? Now what? Now we need to balance our molecular formula first, or our molecular equation. We go through on each side, totaling up how many atoms show up. So lead on the left. How many? On the right. Okay, why is it not 2? I see a 2 right there. That just applies to what's directly in front of it, which is the iodide. Nitrate. That's an eraser. Let me try that again. Nitrate. We have 2 and 1. Is it balanced? What do we do to fix it? We need a 2. Since we're balancing the equation, we must put our number in front of our formula. We can only change the coefficients. You cannot change the formula. Which means to fix, I need to put a 2 here. Now on my product side, it has a 2. Right? Next one. Potassium. Reactant side, how much do we have? Product side, 2. That 2 applies forward to everything after it up to the plus sign, which means we need a 2 in front of the potassium on the right side. Last one, iodide, 2 and 2. The one person that's had me before, I think just one person, looks like just one person, would now know what I will ask, which is, what do we do now? Nope.
Dissociate all strong electrolytes?
Nope. You want to help him out, Thor?
I don't remember. Sorry.
It's fair enough.
I'll find it really good now.
Check it. How many leads?
One on each side.
1 on each side. How many nitrates?
2.
How many potassiums?
2.
How many iodides? And 2. Next step, Thor. Everybody laughed when I did it before. Fine, you don't remember.
Check it again.
Check it again. And again, and again, and again. Every time you go through and do this, you are changing a number, which means you may have changed something you've already balanced. Continue to check it. Okay, you should check it as many times to the point where you are now irritated at me for having told you to check it so many times. Okay? That's when you can stop checking it. And only then. Okay? I will accept that irritation. Wear it like a badge of honor. Now our next step.
Complete ionic equation.
Now what we'll do is we'll move into our complete ionic equation by dissociating our strong electrolytes. As we talked about in class on Monday, we should really change that up. We shouldn't say strong electrolytes, we should say
Aqueous substance?
all aqueous substances. That says aqueous, trust me. So we'll start. Lead nitrate. What happens to lead nitrate? Well, it's aqueous, so I should dissociate it. So what are the ions? I get lead plus 2. And, thank you, I heard you. I'll come back to you in a second. Lead nitrate. This is one of the reasons why I don't like this part of Gen Chem. We have our phases that you also have to include. And then more importantly, how many nitrates do you have? 2. That 2 now comes out front. Right? Because we're now balancing that reaction. Okay? I know that seems weird, but that's what you're doing. You are now going through and you're going to solve 3 new reactions. Right? Making sure that each of those reactions is balanced as you continue through. We then move to our potassium iodide. What happens there when we dissociate potassium iodide?
2K plus 1.
Come back to your 2, but you're right. We have K plus aqueous plus
I plus or minus 1.
I minus aqueous. We now also have to take into consideration that we had a 2 to start with, which means 2K plus, 2I minus. Right? Then what do we do?
We keep the solid together. UPB I2 solid.
We do our next equation, which, sorry, you have to deal with it. K plus aqueous plus nitrate minus aqueous. There's 2 of each of those. What do we do now?
Keep the solid together.
We still have an equation to write here. What is that equation? Sorry, the green's a little bit off, but
PBI2.
right? It's not aqueous, so I can't dissociate it, so my equation just becomes PBI2. I write the exact same thing I started with. That's fine. Hi? There was a little head cock over there. You guys okay?
Yeah.
Okay. We now have our total ionic equation, so now what we can go through and do is cross out anything that shows up the same on both sides. I see PB here, and I see PB here. PB shows up on both sides. That means I can cancel it, right? No. It's not just PB. This isn't just PB, right? This is PB plus 2 aqueous. Does that entire symbol show up on the product side? No, so I can't cancel it. But what I can cancel would be our nitrates and our potassiums. Okay, so if we've been doing good with all our work, and I'm now completely out of space, we can then copy everything down. What was the next one? Iodide? Ooh.
2R.
Just didn't slide right. 2I minus, aqueous goes to PBI2, solid. Okay. As a good last check, since you spent half an hour balancing that equation because I told you to keep checking it, what can you do now at the end? Check your balancing again. How many leads? How many leads? 1. 1. How many iodides? 2 and 2. As long as you didn't make any mistakes, that equation will balance out as well. Okay? Questions on that? Still see some people kind of writing. Oh, I should wait a little bit. I'm good? Okay. So now what we're going to do is move into a subcategory of double replacement reactions. Or as she likes to refer to as that M word. What's the word?
Metathesis.
There we go.
Go
Thank you.
mirror.
It's now recorded. Okay. So what we're looking at now is our acids and bases. Okay. An acid happens to be a species that increases the concentration of H+ when dissolved in water. I personally hate this definition as an organic chemist because what it gets you to focus on is the concentration of H+. This was originally developed by a man named Arrhenius. Anybody know how alive Arrhenius is? He's very dead. Not only is he very dead, he's super, super very dead. Ancient, long time ago. Okay? In the time when we were still using flint to start fire. Okay? We have better tools. We have better definitions. Okay? So one of the things that will adjust from this, Bronsted-Lowry, also dead, but not as dead, so they're a little bit more important. Okay? Change that definition to be proton donor. Well, what is a proton? Okay, it's a subatomic particle, positively charged. Well, Arrhenius' definition said it's the changing the concentration of H+. What is H+? It is a hydrogen atom that is missing an electron. What is a hydrogen atom missing an electron? It's a proton. Okay? It is not the subatomic particle, a proton. It is still technically an atom, so we have to be a little bit careful with that. But those definitions are almost exactly synonymous. Right? What happens when we move up to, never mind, I forgot, there was another slide in there. Okay. As we talked about when we looked at our strong electrolytes, there were certain acids that are defined as strong electrolytes. Why were they strong electrolytes? They completely dissociated into their ions. So in this case, we now look at a strong acid being a species that completely dissociates into H+ and whatever else was left over. Okay. Which means our concentration of H+ ends up sort of becoming really high relative to the amount of material that we started to. Okay. So strong does not necessarily imply concentration. What it's implying is, does that species completely dissociate? Okay? There are 7 strong acids that you are required to know. I have to be a little bit careful with it because it's not my class. I tell students that you should memorize these. I don't know if Dr. Wood insists that you memorize them or not. With a note card, you could probably just write those down as your strong acids on the note card. Okay? Thor, there was a question there?
Doesn't a normal hydrogen atom come with a neutron?
What's its mass? It's 1. What's the mass of a proton? What's the mass of a neutron? 1. So if we had a proton and a neutron, what would the mass of hydrogen be? 2. Hydrogen does not come with a neutron. Deuterium, an isotope of hydrogen, has a neutron. Okay. But hydrogen typically does not have a neutron. Okay, so these are your strong acids. You should memorize these. How do you know it's a strong acid?
It completely dissociates.
It completely dissociates is our definition, and you memorized those 7. What if it's not one of those 7? It's not a strong acid. The opposite of strong is weak.
Okay, so these are the only 7? Okay. That's I mean, it says it on there, but...
These are the 7 you are responsible for, is the better answer to that question. Okay? Let's pretend that slide didn't happen. What do acids react with? Bases. Most people already knew that, so we also have bases, which means we're also going to have to define our base. Okay? And this, again, comes from different conceptual thoughts. Arrhenius went through and noticed that when he dissolved certain species in water and then asked his slave to stick his hand in it, his slave got really pissed off. Okay? There was acid. He then also dissolved some species in water and asked his slave to stick his hand in that too. Unfortunately, slaves are forced to do whatever you tell them to do, or die, which isn't particularly pleasant either, and again burned his hand. So he assumed that they were both the same thing until he mixed them, and all of a sudden something else happened. So that meant that those 2 species had different properties. There's a different characteristic behind it. So he classified 1 as acids and 1 as bases. And within that definition, he noticed that some of our base species increase the concentration of hydroxide. Right? So that says OH. That's not technically hydroxide, right? How do we make that hydroxide?
OH minus.
It needs to be charged, OH minus. Oh, maybe that's a carryover, you think? Yeah, that looks like it was a PC to Mac issue. That charge should have been up there. Okay? Again, this definition is a horribly narrow definition. It really only works within the confines of general chemistry, and I do mean general chemistry applying both 151 and 152. Okay? Bronsted-Lowry, remember, went through and refined our definition of acids. So they also equally refined the definition of base. Any ideas on how they changed it? They focused on the exchange of the proton. So an acid gave up a proton. A base then needs to be accepting of that proton. So that's all that a Bronsted-Lowry definition is. It now is a proton acceptor. Okay? Let's take a look at our hydroxide. Could hydroxide act as a proton acceptor? Well, what is a proton? First off, symbolically, thank you, that was the proper word. Okay. And our hydroxide. Would I expect a reaction here? Why? There's charge. Charge is inherently unstable. So what happens? I take H plus and I put it near OH minus. What happens when I put the H plus next to OH minus? I get the formula HOH, or more commonly known as H2O, or water. What charge do I have on water?
None.
None. This is now a favored reaction because I've lost charge through the course of the reaction. Okay? Charge works really well for organic chemistry. Doesn't work so well for Gen Chem because we don't allow you to show charge ever. Okay? Which is a bit unfortunate, but that's the way it works.
When you're saying strong acids versus weak acids, are weak acids the ones that would, that would give it precipitate, like in the lab, or no?
No. Yeah, your weak acids don't necessarily give a precipitate. Okay, what would happen with your weak acids is it just means it doesn't dissociate as much as your strong acids. Its solubility in water is an entirely separate question. Oops, sorry. Okay. Yeah.
What are the phases? Is that hydrogen gas and OH aqueous?
Hydrogen gas would be what formula? H2.
Yeah.
We're looking at these all in solution. Those charges are not stable on their own. Those would absolutely have to be aqueous. So one would have come from maybe sodium hydroxide. The other one could have come from HCl. Okay. And we would generate water. What phase would we associate with water?
Liquid.
Why not aqueous?
Because water can't be dissolved in water.
Yeah.
Really? Water doesn't dissolve in water.
Yeah.
If I take 2 containers of water and I mix them together, you're telling me those 2 containers don't mix?
You don't
Well, it
dissociate.
makes sense, they just don't separate into ions.
Yeah.
Okay. Dissolving doesn't necessarily mean ions. It means you get a homogeneous mixture. Okay.
So it's aqueous.
But does it really make sense to say water dissolved in water?
No.
No, because it's a pure substance. So instead, we reference it as a liquid because it's a single compound. Okay. Subtle difference within that process. Other questions on it? Well, if we had strong acids, what do we need? Strong bases. How do you know it's a strong base? Okay. This comes from an equally common, whoops, that was supposed to stepwise. That didn't stepwise very well. Your strong bases include all the soluble salts of hydroxide ion. Okay, why hydroxide ion? What was our Arrhenius definition of a base?
Decrease the concentration of OH minus in water.
It did what to the concentration?
Decrease. The increase. Sorry.
It increased the concentration of hydroxide ion. So any species that any salt that we add to water that dissociates and generates hydroxide, there's your base. Okay? The strong base means it completely dissociates into hydroxide. Okay? So how would we know if it was soluble or not? Well, we could pull up our solubility rules. When we look at the solubility rules, under our insoluble, we have hydroxide. Whoops. What are all our exceptions?
Low one.
All of our exceptions are effectively
Group 1.
our strong bases. Neat. Okay. Questions? Okay. So yeah, now it steps. Thanks. Minor rant here, and by minor it's probably pretty major. I hate this figure. Okay? I cannot stress enough on how awful this figure is. Your textbook undoubtedly shows something very similar to this, and it is the worst thing that we could possibly do to you for understanding organic chemistry. Anybody that has to move into organic chemistry will fail at organic chemistry if you draw things like this. Okay? Massively incorrect. Okay? So there's my minor soapbox moment. Ish, if you want to call it minor. What are they showing with that blue arrow?
And H is being donated.
A hydrogen atom is moving. Okay? Believe it or not, no atoms ever move. The only thing that causes a reaction to occur is the exchange of electrons. Showing an arrow like this is saying an atom moves. Never happens. Everything free floats throughout solution. Everything is constantly moving. The only reason why that hydrogen can now be connected to the nitrogen is not because the atom jumps, but because the electrons on the nitrogen share with that hydrogen. That is why it breaks. Okay? Why did they decide to show you this? Because they don't want to spend the time explaining to you a new definition of acids and bases, which is the best definition, the transfer of electrons. Okay? So, in acid-base reactions, if you ever see me again in organic chemistry, I will flip out all over you. Okay? We do not move atoms, we move electrons. Okay, so let's rewrite this equation so that it makes a little bit more sense. We start with our water. And we have our ammonia. Whoops. It's already started drawing it out. Might as well continue all the way. And what we're going to try and do is predict what happens here. Okay, well, we just said the only reason that hydrogen can jump places is because electrons are being shared from somewhere. Where's my electron source? It's a tricky question.
Little dots.
Which little dots? Because there's two sets of little dots. On the nitrogen. The nitrogen is the one sharing the electrons. It shares those electrons with the hydrogen. So if we just draw this out exactly as drawn, which is wrong, by the way, so don't go copying this down, at least not quite yet. What we have now shown is the formation of a bond between the nitrogen and the hydrogen. So we would end up with that structure. Okay, that's all that arrow shows. Does anybody have any problems with the structure shown? It's actually a little bit worse than a compound. It's a horrible compound. Does not exist.
Would not be stable.
Why is it not stable?
Is it because of the electrons and the oxygen?
Think back to drawing your Lewis structures. How many bonds does hydrogen have?
Oh, one.
Hydrogen can only have one bond. Did you guys get this?
Yes.
Did you guys get it on the other side? Okay. Hydrogen can only have one bond. How many bonds are shown to that hydrogen right now? Two. That's a problem. Okay, so how do we fix that? We go back to our starting material and say we have to add some more information. What's that more information? Hydrogen has too many electrons around it, so I have to remove electrons. The electrons I can remove are the electrons in the bond between the oxygen and the hydrogen. Which then means what happens to that line in my product? It disappears. Okay? From 130, you should remember your Lewis structures and assigning formal charges. The charge on the oxygen, if you don't remember that yet, you'll see it again later this semester. The formal charge on the oxygen becomes negative. The formal charge on the nitrogen becomes positive. We now have the products that they're trying to depict. Okay? Please do not pick up atoms and show arrows moving them. Okay? That doesn't work. It's a horrible method. Okay? And it's bad enough that I'll make sure that Dr. Wood knows that I went through and whined about this incessantly. Okay? So that she doesn't pretend to show you this either, because it messes with your understanding of organic. Okay? Yes?
Okay, the only thing that moved it was one proton, right?
So we've changed the bonding pattern of that hydrogen, or that one proton. We changed it by moving the electrons. We did not change the atom's location. We changed the electron locations that made it look like the atom has changed locations. It's a bizarre kind of system, but that's how it works.
When you right there, when you move the hydrogen to the nitrogen, how come you put two dots in replacement?
What does this line represent? Good question. So number one, you didn't ask about the two dots on the nitrogen. Where did those two dots go? Okay, so we got a good question. The two dots on the nitrogen have somehow disappeared in the course of the reaction, and all of a sudden what appeared on our oxygen?
Two dots.
Two dots. Where did those dots go? Where did the dots go on the nitrogen? We said that those electrons moved towards the hydrogen. What's now connecting the hydrogen and the nitrogen in my product?
Those two dots.
A line. What does that line represent?
Two dots.
Two shared electrons. Where did those two dots go? Into that line. Where did the two dots come from on our oxygen in our product?
That bond.
From that line, which was two electrons to make that bond. Since it's no longer a bond, we can show it as the dots. Does that make sense? Good question. Does it make sense?
It does, yeah. Is that part of the Lewis electron dot diagram?
This goes back to Lewis electron dot diagrams, yeah.
That we remember. I just gotta remember.
You guys haven't talked about those yet this semester? Yeah, you will be talking about them eventually. This is one of the repercussions of it. Okay? You move into organic chemistry, study the crap out of that. It's important.
Yes.
Okay. Other questions? Yeah.
On the water, does it matter which hydrogen goes to the oxygen and nitrogen?
Interesting question. Does it matter which hydrogen the nitrogen picked up?
No.
Why not?
Because it was the same hydrogen.
They're the same. There is no difference between them. Why did I pick up the hydrogen on the right side and not the one on the left? It was closer. It was more convenient for me to draw. That is it. Okay? Other questions? Ooh, I feel good about myself. We talked about organic chemistry. I like that. Okay. Neutralization reaction. So now what we can do is look at the overall system for a neutralization reaction. It's the same general concept of what's happening in a double replacement. So if we take a look at a neutralization, my pen works, we have our cation, hydrogen, our anion, chloride, we have our cation, sodium, and our anion, hydroxide. What happens on our double replacement? We exchange the location. So the sodium is now paired with the anion of chloride, and I got H2O. What the heck? How did that happen? That's the same as OH. Which is more correct, HOH or H2O? H2O is technically more correct. Okay? Which one should you do? Whichever one gets you the answer correctly. That's what you should focus on. Okay? I used to always do H2O. I've noticed HOH is a little bit easier and cleaner to see the double replacement reaction. On an exam, I'd write HOH, and if I had more time, I'd come back and change it to H2O.
So a neutralization reaction is a double replacement that ends up with water?
So your textbook is nice on giving you these lovely definitions on what's happening. So if we look at this definition, an acid and base are combined, the products are salt and water. So let's take a look through. We took an acid and a base, we made our salt, there we go, sodium chloride, that's a nice salt. How do we know it's salt? Don't tell me because it's sodium chloride. It's an ionic compound that's aqueous, we've got our salt, and we formed water as our liquid. Right? God, it would be really hard to find an example of an acid-base reaction where that wasn't true. Oh yeah. Our previous slide. In an acid-base reaction, where's the water for our product? Good call. It's not there. Okay? So what's going on with this definition? There's this big, massive caveat.
No, generally.
Generally, when you mix an acid with a base, you end up with a salt and water. Are there exceptions to that? Yes. Okay. Really where this definition holds true is when you mix a strong acid with a strong base. Why? Because a strong acid supplies
H plus.
strong, oh yeah, you're right, I said acid. Strong acid supplies H+, and a strong base supplies
OH minus.
OH-, which means when I mix the two, I get water. Okay? That's where that definition really holds. There are all sorts of other broader reactions that are technically acid-base reactions that are also technically neutralization reactions that don't fit this definition. Okay? So be a little bit more careful when you go through and look at those. The biggest exception that you'll see is when you're looking at bases. There are ways that you can have a base that does not directly supply hydroxide. It can go through a bunch of other secondary reactions. Your big one, ammonia, NH3. Okay? One, and I thought I saw another hand.
Will there always be heat associated with each acid in this reaction?
When you go through and do an acid-base reaction, every single one of them generates heat, which means they are also known as exothermic. Which is why in that safety video, right? You all watched that ACS safety video. They said, always add acid to water, never water to acid, and they poured the water to acid in. You saw that spattering and that violent, massive reaction.
I don't think that happened.
It does happen
Oh, really?
at a much larger scale.
Okay.
On the scale that you would see in that video and in lab, it's so small that you never see that exothermic reaction. It needs to be at a larger scale to actually pick that up. You may also remember, if you watch it again, you see splattering. You're like, oh my gosh, it's splattering, look at that. No, they just spilled to give it the effect that it was spattering. That was about it. Okay, I thought there was a question back here. Yeah.
I was going to ask about the COOH acids, or how that works. Isn't that hydrogen and CHOH? They're also an acid.
You thinking of that one?
No, I thought it said.
Oh, yeah, never mind. I got you. And yes, this is actually an example of that. This is known as, I heard it, say it again, acetic acid. You are responsible for being able to name that, so you should check your nomenclature on that. If we drew out this structure, so this is something else that happens in organic, is we look at structure, not formulas. Formulas are meaningless. And I always forget to draw that one. There's a C there. This functional group is known as carboxylic acid. Sometimes it's abbreviated as COOH. Okay. How do you know if it's an acid or not? In 130 we have the cheat method because we say there's an H in front. That's how you know it's an acid. How do you know? I got nothing for you, unfortunately. Okay. Until you look at structure, it's really hard to define your acids and bases, okay, from a formula. Because I could very easily change that formula for acetic acid to this. Is that still acetic acid? Maybe. It's kind of hard to tell. Formula sucks, so you can't really figure it out. That's still technically an acid. I could also write it as each of those shows varying amounts of information. When it comes to identifying your non-standard acids, practice at this point. Until you actually understand something of structure, you can't really do anything with it. So we could also go through and break that down like we've been doing with all our other ones into the individual ions. HCl being aqueous takes us to our H plus aqueous, our chloride aqueous. Our sodium hydroxide breaks down as well. Our sodium chloride aqueous breaks down. What happens to our H2O? Stays the same because it's not aqueous. Okay? So we see that as that new phase, as the liquid. And that shouldn't be a plus there. That should be an arrow. Okay? Questions on that? So treat your acid-base reactions the same as you would any of your double replacements because they're the same type of reaction. There really is no difference between them.
Wait, are the bottom two one reaction?
Oh, wait a second. That's why there's no arrow there.
Yeah.
Here we go. My bad. So this was your molecular, your total, your net was H plus plus OH minus. Sorry, I thought it was the net that was shown there. Our liquid. And again, you have to be careful. You need to include your charges, absolutely, and you need to include those phases. Okay? Other questions? Thank you. Why is this one included? So when we mix magnesium hydroxide and HCl, yeah, let's just skip over that because I thought it was looking for something else and I'm definitely not seeing what it was looking for there. Maybe it's this. If we did that double replacement, what would our products be? We have magnesium chloride and H2O. Magnesium chloride, soluble or insoluble?
Soluble.
Is it? I actually don't know. It is.
According to the.
Then yeah, I don't know what's going on with that picture. Yeah, something weird's happening there. Right, but we're getting an acid-base reaction. Yeah.
Maybe it's the milk of magnesium. Is the milk of magnesium, is that?
It's magnesium hydroxide. It's supposed to be magnesium hydroxide. So I am not quite sure what that figure is trying to show. Gas-forming reactions. So this is a fun one. Some of our gas-forming reactions look a little bit tricky. So let's take a look at one. Calcium, what's the name of that first compound? Calcium carbonate and hydrochloric acid. Predict the products. So go ahead and write it down, see what you can come up with. I want the products of this reaction.
Yeah, exactly.
I'll give you 30 seconds. I'm going to guess that most of you came up with, hopefully, well, it's color code, why not? Blue, our calcium with our chloride, plus our hydrogen with our carbonate. Should have at least gotten that far. That is going to be wrong. For what reason?
Because they're not balanced.
You haven't balanced your formulas yet. Chloride has a -1 charge, calcium has a +2. We need 2 chlorides to balance out your calcium. Hydrogen has a +1 charge, carbonate has a -2, which means I need 2 hydrogens to balance that out. Okay? We could go through and specify phases on this using your solubility rules. Calcium chloride is, I'm trusting you because I actually don't know that rule. Hydrogen carbonate. Okay. Let's assume we balance the equation. Well, here, we can balance that real quickly. We just need a 2 there, right? Okay, so carbonate, according to your solubility rules, is a solid.
Solid, yeah, never mind.
Guess what? Is this right or wrong? It's wrong. Okay, so it must have been aqueous. So let's fix that and make it aqueous now, right? Guess what? Still wrong.
Is it a liquid?
Nope.
It's a gas.
A gas.
Gas is closer, but it's not a gas.
Oh.
Carbonic acid decomposes.
The water and carbon dioxide.
Well,
So as soon as we form that carbonic acid, it immediately turns into H2O and CO2. What's our phase on H2O?
Liquid.
Liquid. Our phase on CO2?
yes.
Gas. Okay. So there are certain reactions, particularly acid-base reactions, that will form an unstable product that immediately decomposes. Okay. Depending on how nice or mean Dr. Wood is within her individual tests, she may expect you to write H2CO3 as a multiple choice answer when you're looking for CO2. Okay? So it depends on the situation. So you have to be very careful with those reactions. Make sure that you adjust those accordingly. Carbonic acid is one of those. As soon as you see H2CO3, decomposes water CO2 every single time. Okay? Also important for organic chemistry, because if you do this reaction in a closed container, you've just made a bomb
Kaboom.
in your hands. Generally not a good idea.
Can you explain how you figure out that H2CO3 is not stable?
Experiment.
So, I mean,
Yeah, unfortunately it's experiment. That compound is just not stable and it falls apart. So there are some things that you just have to know. This is one of those things.
okay, so going into this, we wouldn't have known that.
True. That's why we brought it up.
So H2CO3 doesn't get a phase?
It does not get a phase. As soon as it's formed, it decomposes. Okay. Are there other ones that do it? Yeah. HCO3 will also do it, also known as, what is HCO3?
Carbonic acid.
HCO3 is not carbonic acid. Carbonic acid is H2CO3. Hydrogen carbonate or bicarbonate.
Oh, yeah.
Okay.
Yeah, we should know
So
this.
sodium bicarbonate or sodium hydrogen carbonate will do the same thing. Why? In that previous reaction, if we just shuttled a single hydrogen across, what would we have made? You would have made HCO3 minus. HCO3 minus is bicarbonate. It reacts in the presence of an acid to form H2CO3, which is what we talked about in that previous slide. That decomposes down into CO2 and water. Okay? So if you see CO3 showing up in an acid-base reaction, CO2 and water. That's the easiest way to, unfortunately, memorize that. CO3 anywhere, you're going to see this decomposition. So that's not too bad. It's just one thing, except there's another. SO3 will do something similarly. Why might never mind, don't answer that question. SO3 just does something similar. Okay? So when it picks up hydrogens, it would form H2SO3. H2SO3 decomposes just like CO2 does, or just like carbonic acid does, into SO2 and H2O. Okay? If you're interested in seeing all the arrows and pushing of electrons and atoms, you can talk to me after class. I got no problem showing you that. But you're not responsible for it. You are responsible for knowing that that is the result. Okay? Questions? Good, because we're moving on. Mainly because I have to. Oxidation and reduction reactions. So in this next sequence, you have what's known as your single replacement reactions. They are more broadly categorized under your oxidation and reduction reactions, okay, or redox. Why do we refer to them as redox and not oxidation reduction, or even just oxidation? It's shorter, so I could just call it red and ox, but we almost always refer to it as redox, not red and ox independently. Why do we smash them together? They happen at the same time. Anytime you have a reduction, you also have an oxidation. You have no choice. That's the way it works. Okay? They have to happen together. Okay? These reactions occur when you exchange electrons. So if your oxidation state changes. Yes, I just introduced a new term. We'll talk about that in a second. So it's when an oxidation is when an atom loses electrons. Well, reduction is the opposite. What's going to happen for a reduction?
Gain.
It's going to have to gain that electron. Okay? Some random definition stuff and some examples. Oxidation typically came from, or as a term, came from the idea of a metal reacting with oxygen. So when it reacts with oxygen, we increase its oxygen content, hence it was oxidized. That's the origin of the oxidation term. Why reduction? Well, you're doing the opposite. Instead of increasing oxygen, we are decreasing oxygen, also known as reducing the amount of oxygen. There's our reduction. Okay? In our single replacement reactions, you'll start with one in its metal or elemental state, and you'll react it with something that's not necessarily in its elemental state, and we get a product where some changes have occurred. We've moved out of the elemental state. Okay? Corrosion is your classic example. So if we take a look at rusting for that equation, iron plus oxygen makes iron oxide. Okay? What happened to the iron in our product? It is now chemically connected to oxygen. Was it chemically connected to oxygen in the reactant? No. So what happened to the iron? It was corroded, yeah?
It oxidized.
It oxidized. If the iron was oxidized, what happened to the oxygen?
Reduced.
It was reduced. So in certain circumstances, we can kind of, by inspection, look at what happens to it. Okay? And ultimately what's happening is this exchange of electrons, which is a bit tricky to classify and work with. Okay? we're looking at this transfer of electrons from one place to another, from one atom to another. And that's what this is referencing here. So, there are rules for being able to understand your oxidation states. Okay? This is an entirely new slide. I didn't like the slide, so I put in my own. Sorry. Okay? Rules. Any atom in its elemental state has a zero oxidation state. Okay? So if I just draw out iron, solid, its oxidation state is now 0. Okay? So it's used as a rule, but it's really not that good of a rule. We've got a better way of looking at that, which comes all the way down to our end. For any monoatomic ion, I'm trying to read what it says, the oxidation number equals the charge on the ion. So if I now switch this from being iron solid, its elemental state, but make it aqueous, well, iron doesn't dissolve in water, but iron ion does. Okay? So this is a monatomic ion. There's only a single atom there. Its oxidation number is the same as the charge. Okay? This is where it can get confusing. Charge and oxidation state and or number are different things, entirely different meanings. Nonmetals typically carry a negative oxidation state. What did nonmetals typically carry as a charge? Nonmetals? They were all typically negative, so it starts to reflect that. Okay? There are some exceptions within those. Oxygen will always carry a -2 charge. Okay? So if I combine chlorine with oxygen, oxygen carries the -2 charge, chlorine changes its oxidation state. Okay? You do encounter some exceptions. I don't know how important those are for you. Hydrogen almost always carries a +1 charge, oxidation number. Okay? Its exception is when it's bound to a metal. Why? What charge do your metals typically carry? A positive. Okay? So if we put hydrogen next to a metal, the metal gives up its electrons, hydrogen accepts it, and it can become negative. Fluorine is a -1 charge. Okay? Other halides will also be -1, except when bound to oxygen. We don't worry about technically fluoride being bound to oxygen because that doesn't happen very often. Okay? The last one is probably the most important rule, and we'll see it show up in a couple of situations. The sum of the oxidation numbers equals the charge on the molecule. That defines everything else, almost everything else. Okay? So let's take a look at some examples. So charge versus oxidation state. Charge is always given to you, every single time. It's the number written in the upper right-hand corner of all formulas. What is the charge on that first example? Well, actually, the one that's circled. Let's do that. That middle one. What's the charge? +2. How do you know that? In the upper right-hand corner, it says +2. How about the next circled one? Okay, so I know that orange thing didn't look very obvious, but we're looking at this one now. What's its charge?
0.
Nothing's written there. It's 0. Okay. Third one, our nitrate. Whoop. Yeah. What's its charge?
+5 and -.
What's its charge?
Negative.
-1. What's the charge on sulfate? -2. Your oxidation state is a numerical representation of the ion imbalance in an element. Okay? Same thing as oxidation number. It only refers to an element, never to a molecule. Okay? So, in our first case here, Cu. What is the oxidation state for Cu?
0.
Okay? This is where I'll get obnoxious. You should solve for the oxidation state. How do we solve? It's the number of the element times the oxidation state plus the number of the element times the oxidation state all the way up, and that must equal the overall charge. So, start with that first one. How many coppers are there? What's the oxidation state? Always solve for the oxidation state, which means what is it? It's X. Good answer. What other element is present? None. What does this have to equal? I like the number, but tell me what a number represents. The charge. What is the charge on that molecule? 0, and we know that because in the upper right-hand corner, nothing was written. Solve for X. What does X equal? 0. So that first rule that we had, anything in its elemental state is 0. Why? Because of that last rule. Next one. What is the oxidation state for Cu plus 2? Well, we go through and solve it the same way. How many coppers are there? What's the oxidation state? X. This has to equal the overall charge, which is plus 2. Solve for X. It's plus 2. Good job. Now the real tricky one. Solve for the oxidation states. What would the answer be? Or how many answers would there be? There are 2 because there are 2 elements. Okay? And remember, this is not the charge. Okay? So ignore what we just talked about. Charge on oxygen in general is -2. Charge on nitrogen? It's one you should memorize, right? -3. If those charges were the oxidation numbers, does this formula add up to the proper charge?
No.
It does not. That's because charge is not oxidation number. Okay? So in our solve, we have how many nitrogens? What's the charge, or sorry, oxidation state of nitrogen? How many oxygens?
3.
What's the oxidation state of oxygen?
-2.
Okay, I'm going to write Y for the moment. We'll come back to that. This has to equal what charge? Careful. It is -1. Okay. We have one equation, 2 unknowns. This is impossible to solve. Until we remember in the back of our head, there was that really important rule. The oxidation state for oxygen is always -2. We know Y equals -2. Solve for X. X equals +5. The oxidation state for nitrogen in nitrate is +5. The oxidation state for oxygen is -2. Okay? Memorize the oxidation state for oxygen. After that, you can pretty much just run off of this nice little equation.
Cool.
You should be able to go through and do it for the sulfur as well in our sulfate. If you check all your work, you should end up getting, assuming I did it correctly, the sulfur being a +6. Can you do this calculation in your head? Yes. When you do it in your head, though, you'll probably do it wrong at least once or twice, and that once or twice will probably happen on the exam. Okay? Write it out. Solve for it. It's not going to take that much extra time. That will guarantee you the correct answers. Okay? Yes.
Is that your own side?
Yes.
Okay.
Like the next 2 or 3 are mine, too.
Oh, no.
Determining oxidation states. We're kind of short on time, and I got to make sure that you guys have enough material for the quiz that's on Monday. So, determining our oxidation states, you should be able to go through and repeat this for every element here. Is the oxidation state for iodine in the reactant the same as the oxidation state for iodine in the product?
No,
Why not?
because the iodine in the product will be 0.
We've changed what atoms it's connected to. Iodine in the product is going to have a 0 oxidation state. So when you go through to determine oxidation states in an individual problem, you have to determine the oxidation state for every single element on the reactant side and every single element on the product. The one sort of exception to that, what's the oxidation state for oxygen on the reactant side? -2. On the product? -2. So as long as you see oxygen bound to any other element except itself, it will have a -2. What's its oxidation state when it's bound to itself? 0, because elemental state. Okay? So we could go through and look at the work on that. That's what I'm going to skip. Here's our answers for all of our oxidation states. What happened to iodine in the course of the reaction? We went from a +5 to a 0. That's nicely stepped, huh? So if we all imagine and close our eyes here for a second and think about wonderful things. Okay, now you can come back to the slides. Iodine started at a +5, and the product it has a 0 oxidation state. How did it go from a positive to a 0? Don't even look at our oxidized or reduced. Just tell me what happened to it. How do we go from positive to 0? What has to happen? We're hearing lost and gained of electrons. So let's take the term loss of electrons. Mathematically, what is a loss? Subtraction. What charge is an electron? If I subtract a negative, what do I get? A positive value. Did iodine lose electrons? It gained electrons because we went from a +5 to a 0. That number was, what happened to 5? It was decreased, also known as reduced. Iodine gained electrons. What happened to the oxygen? Nothing. What happened to the carbon? It went from a +2 to a +4. For it to become more positive, it had to lose electrons. Okay? How else could you decide that carbon was or lost electrons? What did we say? Never mind, let's do this. We can now define these shifts of our electrons. The loss of electrons is known as oxidation. How could we look at the reaction and immediately say carbon was oxidized? What did we say oxidation was? Yes? What else did we say it was? Nope. Reacting with oxygen. What happened to the carbon in our reactant? It was carbon monoxide and it became carbon dioxide. We increased the amount of oxygens attached to the carbon, which means the carbon had to have been oxidized. That doesn't always work because you don't always see oxygen, but it gets you pretty close. You need to know the difference between these. You need to make sure loss of electrons is tied to oxidation and the gain of electrons is tied to reduction. However you decide to do that is up to you. My preference is Leo says Gur. Because Leo, anybody born in August? What is Leo? A lion. Leo the lion. And lions are big cats. And what do cats do? Grrr. There you go. Leo the lion says grrr. The other one that is common that you'll hear around campus is oxidation is loss of electrons or oil, and reduction is gain of electrons, which is rig. No offense, I think that one's dumb. I like Leo says grrr. Okay. After all of that, so when you look at a reaction, you're going to have to predict, was it oxidized, what was reduced, and identify all those species. To do that, you have to go through and determine the oxidation states. So that's a lot of extra work. Okay? On top of all of that, we end up throwing in some new terms at you. An oxidizing agent. Okay? What is an oxidizing agent? Or even an oxidant?
It's what's being reduced.
It causes something else to be oxidized. Well, if it caused something else to be oxidized, what happened to it? It was reduced. An oxidizing agent is reduced. A reducing agent is oxidized. Because it wasn't confusing enough. Okay? So watch out for those differentials. At that point, I think you've got enough material to be able to do fine on the quiz. You're identifying your redox reactions. Your quiz is primarily on redox and balancing and the stuff that's been covered up to this point. I think you'll do awesome on it if you review all this information.